I'd like to thank the organizers for inviting me to this very interesting workshop. It is unfortunate that we cannot meet in person, but let's see what we can do with this online version. My name is Hyeonsik CHEONG. I'm going to talk about the optical spectroscopy of 2D antiferromagnetic materials. And my background is semiconductor physics, the spectroscopy of semiconductors. So this magnetic material is very new to me. So I'm just learning a lot of things about the spins. So let me start. Okay, right. The magnetism in low dimensions is a kind of very interesting topic. And a long time ago, Hans Bethe proved mathematically that no magnetic ordering is possible in one dimension. And in 2 dimensions and higher, things are more interesting. And if you write down the magnetic Hamiltonian in a simple form like this, there is a very famous Mermin-Wagner theorem that says the ferromagnetic or antiferromagnetic ordering is not possible in 1 or 2 dimensions if the interactions are isotropic. So in Heisenberg type system, where the in-plane exchange interaction and the out-of-plane exchange interaction is the same, no magnetic ordering is possible in 2 dimensions. In the Ising model, where the XY component is 0, there is also the famous Onsaga solution that says magnetic ordering is possible in the 2-dimensional limit. Now, in the XY model, where the exchange interaction is mostly in the plane, things get very interesting. And here we get what's called BKT transition, and some exotic things are supposed to happen. And everyone in this workshop probably knows these 2 famous papers now published in 2017 on ferromagnetic 2-dimensional materials. And actually, we actually published our first work on antiferromagnetic material 1 year before, but ours didn't get as much attention. So to do justice to antiferromagnetic material, let me show you our result on different antiferromagnetic materials in this talk. Now, the antiferromagnetic materials, the study of antiferromagnetic materials in 2 dimensions is quite complicated. There are experimental difficulties because there is no net magnetic moment. One cannot use tools that measure the magnetic moments, such as the magneto-optical Kerr effect measurements. And conventional tools to study antiferromagnetism, such as neutron scattering, are not adequate because of the very small sample volume. So you have to resort to a kind of indirect measures. And here comes the optical spectroscopy and Raman scattering in particular. And I have to mention here that Raman scattering does not always work. For some materials it works, some materials it doesn't work. So you have to be lucky, I guess, to be able to use Raman scattering to probe antiferromagnetic ordering in 2-dimensional materials. The material system that we studied is transition metal phosphorus trichalcogenides, TMPX3, and these are the materials with compounds with the transition metals and the phosphorus and chalcogens. And among these materials, these are the 3 compounds that we studied: iron PS3, nickel PS3, and manganese PS3. I know other people use, for example, selenites as well. And good thing about this system is that the crystal structures of these three materials are exactly the same, except for the transition metal elements. However, the magnetic structures are quite different. So INPS3 is an Ising type antiferromagnet. Nickel PS3 is the XXZ type antiferromagnet, which behaves like XY system in the low temperatures. And manganese PS3 is a Heisenberg type. So by studying these three materials, we can study the different aspects of the magnetic ordering depending on different types of interactions. So these are the contents. I'll go through in historical order, the IMPS3, that was the first work in our group, and then nickel PS3 and manganese PS3, covering Ising and XXZ and Heisenberg type antiferromagnets. And in the end, I'll just, this is not Raman work, but our recent photoluminescence work that's just published a couple of weeks ago. So I'll just throw it in if time allows. So first, this Ising type antiferromagnet INPS3. INPS3 has a honeycomb arrangement of ion atoms, and this is the bulk material is monoclinic because the stacking is slightly offset, and the monolayer is a hexagonal material. As I said, this structure is identical to in nickel PS3 and manganese PS3. And long time ago, people already measured the Raman spectrum of this material at room temperature and low temperature, and they observed some differences. But I guess the correlation between the Raman spectrum and the antiferromagnetic phase transition was not clearly, well, seriously looked at. So we started with the bulk INPS3. And here we are comparing Raman spectrum of bulk material at room temperature and at low temperature, below the nail temperature, and in two different polarizations, just to show some differences. And there are two groups of phonon modes. The first group, the higher frequency modes, these are mostly due to vibrations of phosphorus and sulfur atoms. And in fact, these modes are more or less similar in all three of these materials. And so this, for example, this is one of the modes that are involved here. And the lower frequency phonon modes involve the vibrations of transition metals. And in particular, this P1A involves the vibrations of the ion atoms, so they are likely to be affected by magnetic ordering. So this is a temperature dependence of the Raman spectrum in bulk material. So as we cool down the material, the most spectacular change occurs in the lowest frequency Raman peak, and this low frequency mode at room temperature is more like a broad band, but at low temperature it becomes very sharp, and it actually becomes a series of at least 4 peaks. And if we plot the intensity of this lowest frequency peak as a function of temperature on the right, this red one, it correlates with the susceptibility data almost perfectly. So there is a clear correlation between the susceptibility and the Raman intensities of this lowest frequency peak. So we are going to use this peak as the indicator of the magnetic ordering. By the way, there is a report, I think from the NIST group, that show that one of these peaks correspond to magnons, but that's not the topic of my studies. And so now we are studying few layer FePS3. I'm just showing the monolayer and quite thick bulk like 51 nanometer thick sample. And even in monolayer, you can see the emergence of this sharp peak at the lowest frequency phonon mode. So this signature of antiferromagnetic phase transition appears even in the case of monolayer, and we actually studied 1, 2, 3, 4, 5, and for different thicknesses, and we all observed the similar behavior. And although the signal to noise is not as good in the very thin samples, we could pull out the approximate phase transition temperature from the dependence of this lowest frequency peak. And here is the result. It shows that the 118 Kelvin is the known nail temperature of this material. There could be some slight offset due to just the cryogenics of our system, but the phase transition temperature that we measure is more or less constant across all the thickness. So the first result from FePS3 is that Ising type antiferromagnetic ordering is sustained down to the monolayer, and the transition temperature does not change much with the thickness, which indicates that the interlayer interaction in this case has little effect on the magnetic ordering. Our next topic is nickel PS3. This is XXZ type, and there's some theory that says at low temperature it behaves like XY type. So the crystal structure is identical to FePS3. We just replace iron with the nickel. And here I'm comparing the Raman spectra measured at room temperature and at low temperature, and in two different polarizations, okay, parallel and cross polarizations. Now, unlike in the case of FePS3, the changes in the spectrum are quite rich. First of all, we can see this broad peak emerging at low temperature, which is due to the two magnon scattering. And then we also observed that at very low frequencies, this signal due to the what's called quasi-elastic scattering is suppressed at low temperature as the system is ordered. The spin fluctuation that causes this quasi-elastic scattering is suppressed. And also this P9, which is symmetric at room temperature, shows very strong phonon resonance line shape. And if you look very carefully, in two different polarizations, the position of P2 is different at low temperature. At room temperature, they overlap, but at low temperature, the peak positions are different in two different polarizations, which means that at low temperature, in two different polarizations, we are seeing two different Raman modes that are split. So the splitting of P2 is also is correlated with the magnetic ordering. So first, this is the temperature dependence of the Raman spectrum, and from the room temperature to the low temperature. And here we are plotting the spectral weight of the quasi-elastic scattering, the phonon resonance, the strength, and two magnet peak position, width, and intensity. And this pink band is the bulk anneal temperature. And these values show some correlation, but the correlations are not very dramatic. And then we look at the this peak splitting of P2. These are the spectra measured in two different polarizations to show the splitting. And if you look at it higher resolution, you can clearly see this splitting. And we actually saw the similar splitting in P6, but P6, this peak is always split, even at room temperature. So it has nothing to do with the magnetic ordering. But P2 is single peak at room temperature, and it shows splitting. And if you plot the splitting of this P2 and overlay it with the susceptibility data, here's the near temperature. You can see that there's a very good correlation with the magnetic ordering. So we are going to use this as an indicator of magnetic ordering. And in fact, our theoretician explained to us that this P2 is actually two modes, AG and BG modes, that are very nearly degenerate at room temperature. But when the system is ordered, in the AG mode, the vibration is across the magnetic ordering direction, and BG mode is in the direction of the magnetic ordering, so that makes that slight energy difference and split the peak. So now here I'm showing the two series of temperature-dependent Raman spectra for the bulk material and monolayer. And in the monolayer, the trends are actually quite different. And for example, the magnon peak at the lowest temperature in the bulk is much stronger, and it is there even in the monolayer case. But and also this phonon line shape is there, but this peak is symmetric in the case of monolayer. So if you plot these quantities, to magnon peak position, to magnon peak width, normalized intensity, and the phonon resonance, and black is the bulk, red is the monolayer, the trend seems to be different. And if you compare the data for all other thicknesses, 2, 3, 4, and so on, they overlay more or less with the bulk data, but the monolayer seem to be different. So at this point, we can say there's no significant dependence on thickness, 2 layers or thicker, but monolayer seems to be different. And then here is the comparison of the P2 for the 2-layer case and monolayer case, and you can clearly see that even in 2 cases, we see a clear difference in the peak position in 2 polarizations, but this P2 is exactly the same position. So if you plot the splitting of P2 as for different thickness, you can see that the nail temperature goes down slightly, down to 2 layers, but monolayer shows no indication of magnetic ordering. And so if you plot the estimated transition temperature, it is more or less same, down to roughly 4 layers, and 3 and 2 layers is suppressed a little bit, and in monolayer, we do not observe magnetic ordering. Then we noticed that in the quasi-elastic scattering data, we see some interesting trend. In the parallel polarization, the quasi-elastic scattering signals just simply decrease as we lower the temperature. But in the cross polarization, we don't understand why. This quasi-elastic scattering is enhanced near the phase transition temperature. And this is always true for 3-layer and 2-layer, and bulk, of course. However, in the monolayer, that enhancement, you have to look at this cross-polarization data, there's no quasi-elastic scattering data at room temperature, or very little, but then at low temperature, it is enhanced. So what is happening in monolayer at the lowest temperature is similar to what is happening in thick samples near the transition temperature, which indicates that the transition temperature for the monolayer case is lower than the lowest temperature that we measured. And so here is the plot of that the spectral rate of quasi-elastic scattering for different layers: 9-layer, 3-layer, 2-layer, monolayer, and it shows a small peak near the near temperature, but in the case of monolayer, it just keeps increasing and looks like the transition temperature is the 0 Kelvin. So for nickel PS3, we can say that the antiferromagnetic ordering happens down to 2 layers, and the transition temperature is almost independent of the thickness, and it's slightly suppressed in the case of 2-layer, but in monolayer it is suppressed significantly. So we can say that in XXZ or XY antiferromagnetic, the magnetic ordering becomes very fragile in the two-dimensional limit of monolayer. Now the next is a Heisenberg type antiferromagnetic mangan PS3. Now in Heisenberg type isotropic system, because of the Mormin-Wagner theorem, we would expect that the magnetic ordering would become very fragile as we reduce the thickness. And so we expected that the transition temperature will start to go down as we thin the sample. But there was some, the results are a little slightly different from our expectations. Here, we actually, experimentally, this was the most difficult case because the signal was very small. And this is a comparison of room temperature and low temperature data, and not much difference. And if you look at very carefully, there's 2 changes. One is this P1 disappears, but it turns out to be not related to magnetic ordering, but to band structure changes. And P2 redshifts at low temperature. Now, all the other peaks slightly blue shifts because of the thermal effect, but this one shows redshift. So if we measure it carefully as a function of temperature, we see that it blue shifts slightly as the temperature goes down, and all of a sudden it becomes very broad, and then it re-emerges at a slightly lower frequency. And if you plot its position and the width as a function of temperature, here the red is the near temperature. This blue is something else called a spin flap, something like that. And that blue actually corresponds to the maximum of the susceptibility, and this is the near temperature. And we can see that the increase of the width and the decrease of the position correlates with this near temperature. Here, we don't know whether this slight offset is real or due to experimental error. And this vibration mode is related to the vibration of manganese atom. So, one can understand that the magnetic ordering will change its vibration mode. And after we published our first data, we measured different thicknesses, but because this P2 is extremely weak, typically 0.1 count per second for thin layers, we had some difficulties. Anyway, here are the results for 3, 4, 5, 7, 8 layers and bulk layer. And this is the summary. This shows the width of different thickness as a function of temperature, and 3, 4, 5, 7, 8 layers. And if you pull out the transition temperature from this data, shows that the transition temperature indeed goes down to 3. And in our first experiment, first paper, we show that in 2 layer, even in 2 layer, at the lowest temperature, we had the indication of magnetic ordering. But in this follow-up work, we couldn't pull out the near temperature for the 2 layer. So it's somewhere here. But initially, we expected that this will go down like that, but it doesn't happen like this. So even in the case of Heisenberg type mangan PS3, the magnetic ordering is sustained to some degree. So we observed antiferromagnetic ordering in mangan PS3 down to 2 layers, and the transition temperature decreases somewhat for thinner layers. By the way, Suyeon Lim, my student, will present this this work on mangan PS3 later today in poster room 15. So please go there. And I guess I have only a few minutes. Also, by the way, we published a review paper on this. So if you're interested, you can look up this paper. And this last part, I'll just briefly mention. This is nickel PS3, and this is from bulk nickel PS3. We measured the photoluminescence of nickel PS3. And these are, well, combination of photoluminescence and Raman. So basically, we use different lasers and just measure what's happening in the very broad energy range. So these sharp peaks near the laser lines are the Raman signals. However, you can notice that there's a very sharp peak that does not shift with the laser, and some series of signals are related to that. And that shows up even for the lowest energy excitation of 1.58 electron volt. This is quite remarkable because in the optical absorption data, the optical band gap of this material is supposed to be approximately 1.8 electron volt. So even for sub-band gap excitation, we could see this sharp peak. Now, normally, as a semiconductor physicist, I would my immediate reaction is this is some kind of deep defect. However, if you measure it with a very high resolution spectrometer, you could see that this peak, this is the peak, and there's the 2 other peaks, kind of satellite peaks, we don't know what they are. It's extremely sharp. It's about 0.4 MeV. And its width is actually, it decreases with temperature, and it reaches this very sharp state at low temperatures. And you could see this same sharp peak down to 3 layers. And what is interesting is in the case of absorption spectrum, we see the same peak. Now, if this signal is from a defect, you wouldn't see it in absorption spectrum because the density of state for defect state is simply too small. And the fact that you're seeing the same signal in photoluminescence and absorption indicates that this is from some real state. And even in the case of resonant inelastic X-ray scattering, we see the same peak, and it shows a very sharp in the RIXS spectra. So the fact that this peak is extremely sharp is very interesting because we are using a laser spot of about 50 micrometers in diameter. So we are observing a large ensemble of whatever the light source, whatever the source that gives this signal. And the fact that it's very sharp indicates there is some kind of coherence involved. And we see that this emergence of this sharp transition correlates very well with the antiferromagnetic ordering. So we think this is some transition that's stabilized by the magnetic ordering, and our theoretical collaborators came up with a very complicated explanation. I'm not going to go into that because my time is already up. So if you're interested, you can look up our recent paper here. So here are my collaborators. Jae-Gun Park is the driving force behind all this work. He provides materials and the inspiration. And Choran Park and Young-Woo Son did the theoretical work along with the Kwon Sang-Jeon, and Jae-Hoon Kim's group did the optical absorption. And I have all the nice discussions. And here are my students. The picture was taken a while ago. The INPS3 work was done by Jae-Woong Lee, who's now a professor at Aju University. And the nickel PS3 work was done by Kang-won Kim. Now he's working at Samsung. And the mangan PS3 work is done by Soo-yeon Lim, who will present her poster later this afternoon. Thank you very much.